Thank you, Max, and thank you very much to the organizers for putting together this very nice seminar series. I'm happy to talk today about some work that appeared last December, together with which we did together with Matilda, Sanjay, Ethan, Kamran, and Kai. And the point of this work is to figure out why we actually see dualities in string theory, in quantum gravity, and figure out what are kind of the minimal principles that we need to impose on these EFTs to explain why these dualities are there, in what form they are there. And precisely we'll tie this to some particular finiteness criteria that I'll explain in this talk. So first things first, what is the plan for the talk? So as I said, the goal is to explore the role of dualities in quantum gravity. But first, I'll tell you a little bit about what these dualities actually are. Like we can have non-self dualities where we relate different theories, but we'll focus mostly on self dualities where we relate where different points in moduli spaces are related the same theory. Then I'll explain a little bit how these dualities can be tied to a certain notion of compactifiability for the moduli space, which basically says something about what the volume of the moduli space can do as we go a large distance. And then I'll conclude by giving you a bottom-up argument from 1D quantum mechanics, why moduli spaces should have these compactifiable properties, and how you can actually argue for this from finiteness of these 1D systems. Okay. So first things first, what are dualities in effective field theories that come from string theory or arise in quantum gravity? So let me start with kind of like the typical cartoon where we have all the different string theories and 10 dimensions we know. Some, as I foreshadowed, are related under dualities where in one weakly coupled regime of one theory or strongly coupled regime of one theory, we discover a weakly coupled description of another theory. But in other limits, what we may have is that actually, like say type 2B string theory, that actually if we go from weak to strong coupling, we actually recover the same string in the strong coupling limit. And this is what I'll focus most on today, because all of this information about self-dualities is of course reflected in the moduli space of these theories. So saying that we go from weak coupling to strong coupling and we identify these two different patches, of course, says something about what this moduli space actually looks like if we quotient out by these sort of dualities. So the typical effective action that we write down is, well, we have some Ricci scalar, we have a metric from the kinetic terms that we use to compute a distance, and we can have some further couplings for, say, gauge fields. All of these are parameterized by the scalar fields, by these massless modes of the theory. In principle, of course, you could consider, especially with less supersymmetry, a scalar potential on top, but for the purposes of this talk, there is no scalar potential turned on. So we focus mostly on like n equals 2 supercharges in 4D or higher. So then what do we know? Well, one conjecture that says a lot about the physics of these moduli spaces is that as we go a large distance in these moduli spaces, there is an infinite tower of states that should be becoming exponentially light with this distance in Planck units. And this has been tested to a great extent in Calabi-Yau compactifications, where kind of the picture that we've emerged upon is formalized. Let me see if I can show my cursor. Sorry. Okay, anyway, yeah, the cursor doesn't seem to be working now, even though it did before. But anyway, in this latter work, it was very nicely explained that as you take an infinite distance limit, it can be explained as coming from two types. Either you have a string that becomes tensionless as the same scale as the higher as the compactification manifold, or you're taking really a decompactification limit to a higher dimensional theory. And that's why they coined it emergent string conjecture. So now, what does this mean for dualities? Well, let's say that we have 2 points in the theory, and well, maybe from point A to point B, we need to reshuffle some states because one is a weak coupling limit, the other is a strong coupling limit, where we need to maybe relabel some of the states. Now, a duality means that if we take the Lagrangian and we take the spectrum and we reshuffle everything according to some appropriate duality transformation, say some symplectic transformation for the electromagnetic group, like SL2Z in 10D, type 2B, then we find that we can reshuffle everything accordingly and relabel everything such that we recover the same theory. So this really holds not just for the metric, where of course for type 2B, SL2Z, it has like a full SL2R isometry, but also for all the other couplings that we write down, higher derivative corrections, and also the full spectrum of states that's being populated. All of these things should be invariant as you go from one point to the other, and then that tells us that we should quotient out by a duality. So to put this in terms of a picture, it means that if we take the left half and the right half, we fold these on top of each other, which is this quotienting by the duality group. And even though the non-quotiented moduli space might have had interesting curvature properties or topological properties, the expectation is that, well, the curvature can remain non-trivial, but the expectation is that the non-trivial topology of those moduli space really comes from only the duality group, which was formalized in the Mark moduli space conjecture last year. So on the other hand, we can think of dualities as a gauge symmetry, where we say we shift some kind of axion field, which is a scalar living in this moduli space, and we shift it by a discrete angle as we go around. And then we find that this gives rise to a gauge symmetry in effective theory. So shifting this axion corresponds to the action on the moduli fields. If we go to one of these fixed points, say we shift tau by a third root of unity, if we go to this fixed point, then we have an enhanced gauge symmetry, but only at this particular point. Whereas generically, if we're in the interior of the moduli space, this gauge symmetry will be spontaneously broken. Also, dualities around different points in the moduli space may not commute with one another. Say we go take the Z3 in the right lower corner or the Z in the right upper corner, they may not commute and they generate thereby a complicated non-abelian group, particular to the example that you're working with.
Damian, can I ask a quick question?
Yeah, of course.
So you're saying that dualities are spontaneously broken -1 form symmetries, and so for instance, sometimes we can get dualities when we compactify by actions of the diffeomorphism group of the higher dimensional theory. So in particular, higher dimensional interpretation of dualities is often diffeomorphisms. So would you say that these diffeomorphisms are also -1 form symmetries? I would say they are 0 form.
So I'm always mixing up the counting here, but what do you have in mind, like as an example here?
I guess diffeomorphisms we gauge, right? They're gauged by gravity, but they are like 0 form symmetries, like they act on local fields and so on and so forth.
Same here, I think. I think that's what he means here too.
Okay.
Yeah. And I think maybe a final thing that I didn't say is that you need not see all the dualities from the point of view of the moduli space. For instance, in type 2B, there is this difference between having SL2Z or the projective SL2Z. And you wouldn't see the projective part, like the overall -1 acting on the moduli space, as well as maybe more complicated parts related to the fermions. But For the purposes of this talk, of course, since we'll be interested in the volumes of the moduli space later on, we really cannot say much from that perspective about that part of the duality group. Just about the actual dualities that see the moduli space. So now that was the action on the moduli space. But of course, we don't just have moduli in our theory, but we have more general lattices of states. So for anything, any particle or any brane that has codimension larger than 2, there's just a very straightforward linear action where you take your charge vector, you apply the transformation matrix of your duality group in this linear way, just by multiplying with the charges. Whereas a more complicated part of the spectrum is given by the codimension 2 states, where as we go around, one of these is in 4D an axionic string, in 10D these would be a Severn brane. As we go around this object, we find that it implements a non-trivial duality transformation. Now, while that action on the states as we go around is linear, if we were to take this vortex V around this vortex V twiddle, we find that we have a non-trivial transformation rule, which acts in this conjugate way, which at the level of the vortices means that there is now this nonlinear action. And the statement of completeness for the level of this duality group now means that these duality or the absence of global symmetries, I should rather say, implies that these duality vortices should really be dynamical objects in their theory, by which I mean that they really should be finite tension objects with respect to the cutoff of your theory. Okay, so having said all these things from a general perspective, let's now specialize to an example that most of us will be familiar with. So let's take 10-dimensional type 2B. We have an axion, we have a dilaton, we combine it in the axiodilaton with this standard hyperbolic metric. And the duality group is the familiar SL2Z, by which we quotient out. It acts in this way on the moduli, and the T transformation allows us to fix to this finite strip between -1/2 and 1/2, whereas S duality relates everything where the absolute value of tau is smaller than 1 to the part where it's bigger than 1, corresponding now to this usual keyhole domain that you're all familiar with. Similarly, it acts on higher form gauge fields in this way, leaves the R4 form invariant, and all of this axionic string, Severn brane stuff for the duality vortices now applies to the PQ Severn branes, where if you were to take, say, the standard T transformation corresponding to a D Severn brane, you can generalize it into this generalized PQ Severn brane string, Severn brane object, in this way. And now here you would have these conjugation rules for dragging them around each other and all of these kind of behaviors. Okay. Any questions about this general part about dualities? What do they look like? And what do they do to the states and these sort of things? If not, then let me move to the second part and tie these dualities to the volume of the moduli space. So let's say we fix a point in the middle of the moduli space, phi 0, where precisely doesn't really matter. And then we go out a distance delta from this point. And then we consider this full region, this geodesic ball of distance delta that contains this point, related to this point. Then the natural question to ask is, how does the volume of the moduli space of this geodesic ball now grow with respect to delta? And this is precisely where this key compactifiability criterion comes in, which is demanding that the volume of this geodesic ball, distance delta, can grow polynomially in delta up to the dimension of the moduli space, but no faster. So something like the dimension +2 would not be allowed, but also something like an exponential growth in the volume of the volume with delta would not be allowed. And maybe a weaker but slightly similar version that you can compare this with is that the area of the boundary with respect to the volume of the bulk should always go to 0 asymptotically. And I say weaker here because this criterion would allow for any polynomial growth, but our finiteness argument really indicates this sharp bound with the dimension of the moduli space as an exponent. Another way of saying it is that the volume of the moduli space can grow as fast as Euclidean space of the same dimension, but no faster.
So, Damian, can I quickly ask a clarification? So there's some. So this is a bit like saying that there's some curvature which cannot be positive in the moduli space, right? Because positive curvature usually means that the volume grows faster than the area, right?
Negative curvature, yeah, yeah, that's right.
Yeah.
Well, it can be negatively curved. In fact, that's how I try to separate it. You can have flat moduli spaces with few dualities, or you can have typically large parts of the moduli space that are negatively curved. But in that case, you will need many dualities. And that's actually where this whole compactifiability criterion is the strongest. Because in that case, in these negatively curved spaces, you need dualities to satisfy this bound.
Okay.
I'll do this explicitly in a minute for type 2b with SL2Z. And then we see precisely how it works, which is like the standard upper half plane, a negatively curved space with hyperbolic metric, and where if we wouldn't have the right amount of dualities, we would see an exponentially growing volume. Yeah, so a convenient way to sort the moduli spaces is, on the one hand, we can have flat moduli spaces. They will have not many dualities, and even without the dualities, they would have a polynomial volume growth. Maybe I should first say that you might have expected that the volume of the moduli space would be finite, because in many cases that we know, like vector multiplet moduli spaces in 4D coming from Calabi-Yau compactifications, all of these moduli spaces are known to be finite, but there's a very easy 10D type 2a counterexample, which is just the real line, which is parameterized by the dilaton here. And the volume of this moduli space of this geodesic ball will just grow linearly in delta, since we're just talking about the volume of a line inside the real line, of a line segment inside the real line. Similarly, if we take M theory and were to compactify it on a Klein bottle, we would have the two-dimensional real space quotiented by a Z2. There you would have a volume that grows quadratically. So again, we find that this Euclidean volume growth can happen also with higher exponents than just linear. So on the other hand, we can consider curved moduli spaces. These will be mostly negatively curved. There are some like small regions of the moduli space where you can have a positive curvature divergence. And this was recently very nicely understood in terms of field theory sectors that are decoupling as you take the gravity decoupling limit. But the general feature of these negatively curved moduli spaces is that precisely because you have this exponential volume growth naively, that is compensated by the presence of many dualities, infinitely many dualities that quotient it to a finite volume space. So how does that work for type 2b? Well, we have the typical upper half plane. We modeled out by SL2Z. The upper half plane would have had an infinite volume or an exponentially growing volume in delta. But as we quotient by SL2Z, we find that the volume actually turns out to be just a finite number pi over 6. Similarly, if we take M theory on tori, so these are maximal supergravity theories, maximal supersymmetry, there we find that the volume is always finite of these kind of moduli spaces. And the reason is just that if you take these SOPQ, these symmetric spaces as moduli spaces, and you quotient them in this way, it's just the fact that these kind of moduli spaces, as long as the duality group is SOPQZ, that these will have an infinite, a finite volume. And similarly for type 2b, if you compactify it on a Calabi-Yau threefold and look at the vectors, this moduli space corresponds to the complex structure moduli space of the Calabi-Yau threefold. And for these geometric moduli spaces, it has also been shown that the volumes are always finite. And in fact, very nice rational numbers, as we'll see in a few examples in a minute. Okay, but as promised, let me do a non-example. So let's say we get type 2b, but we didn't know about all of its dualities. But we were clever enough to figure out that tau going to tau plus 1, so the standard T transformation was a duality. Then the duality group would be this gamma uni, the unipotent group, where we just shift the axion by integers. And then the volume corresponds to this strip in the middle. So now let's compute the volume of this moduli space. So if we go out the distance delta, the upper part corresponds to tau2 equals to, or dilaton equals to e to the delta, the lower part e to the minus delta. And if we compute actually the volume of the space, we see that from this lower part of the moduli space, so the part that approaches the real line, we actually pick up an exponentially large volume for this moduli space. So the lower part contributes, if you do the integral on e to the delta, the lower part on e to the minus delta. So the volume is really growing exponentially, which means that this case wouldn't be compactifiable. In other words, we really missed some of the key dualities for this effective field theory, for this theory. And it tells you that really we need non-trivial S dualities to cut out the lower part of this moduli space, to relate the upper part to the lower part. So that's really a key feature or a key prediction, post-diction of this compactifiability, that you need an S duality to render the volume growth polynomial. And another thing that we take away from this is that just this unipotent, this upper triangular duality group is a bad duality group. We need more. And we can actually make a little bit more precise why I call this duality group a bad duality group. And we'll motivate this in a second. But the condition is that a good duality group in quantum gravity needs to have a semi-simple representation. So what does that mean? So let's think of V as the spectrum of states. Let's forget about these funky duality vortices for the moment. And this spectrum of states needs to be possible to decompose into irreducible subrepresentations. And now, how does this precisely constrain the duality group? So let's take this definition and let's apply it to this upper triangular duality group that we just saw. Well, actually, no, sorry. Let me first talk a little bit about it generally. So how can you think of this more intuitively? So say that you divide your spectrum in some subsectors of charges, say A and B. Then in the non-semi-simple case, it means that there are some duality transformations that allow us to map some charges A to B, and maybe B onto itself, but there's no way to map it back. Whereas in the semi-simple case, you can always, if you can map A or change A into B, you can always map B back into A. So a little bit more concretely, if we take the previous example of this upper triangular group, so we have the electric states, 1, 0, we have the magnetic states, 0, 1, and the duality transformation that we have can only map the magnetic states into electric states. but there's no way to act in the other way. So there's no democratic action, if you wish, for the duality group, and semi-simplicity of the representation of the duality group precisely tells you that it should act in this democratic way.
Sorry, Damian, can I ask a quick question?
Yeah, of course.
So the semi-simplicity condition, you're motivating essentially that you can decompose into reducible representations, and you're explaining essentially that in this case there would be no inverse, right? For the from magnetic to electric and not electromagnetic. But physical states, and the way you presented here, we typically assume they transform into unitary representations of the duality group. And unitary representations are always irreducible. So for instance, for the integers, you would never get this representation for physical states. You would always get the one-dimensional representations, which are representing the generator by a phase, which is rational number.
But SL2Z is sorry, I'm a little bit confused by what you're saying. So SL2Z would be a non-unitary group. And say we take for SL2Z the standard spectrum, so just like the PQ strings. So that would be a Z-squared lattice. You're saying that you're asking if that still gives you a unitary representation for the group?
Yeah, I think that once you take into account.
But that would be just the standard representation for SL2Z as 2x2 matrices, and that is not a unitary representation.
And stuff. I'm just saying, like in a, when you have a Hilbert space. So, for strings and stuff, they have infinite energies, but you could always compactify in some dimensions so that,
Right. So it is true that there is still a notion of a unitary product for the spectrum of states. And as you say, it is very important that this is a moduli-dependent product. So it's the usual kind of PQ string tension, for instance, P plus Q tau over tau 2 squared. That is still some notion of unitarity. That's right.
Yeah. And so unitarity implies irreducibility of the representations, no?
Right.
Because they embed into n for some n and then even infinity.
Right.
Yeah.
So precisely, let me say, how do I say this? So we'll be showing roughly what you're saying, so that intuitive statement about having a unitary metric, or rather we won't do it from this metric that you're talking about, but we'll do it from this compactifiability criterion, actually in very specific settings. So in these 4D n equals 2 supergravities from Calabi-Yau, you can really prove that if you assume compactifiability of the moduli space, so you from that you get that the representation of the duality group has to be semi-simple.
Okay.
And the precise proof of that relies a little bit on some. Well, I'll get into that in a second.
Okay, but then,
and if I don't, please ask me again.
Good. So just to understand, there's no independent. So it's not that semi-simplicity is like a different way you can argue for the same thing. It's just something that is mathematically equivalent in some setups.
Yeah. So mathematically, in very particular settings, it indeed comes from compactifiability, and it's an interesting question whether there is a more general argument just based on some kind of unitarity arguments or rescuing unitarity, whether semi-simplicity is a general feature of duality groups.
Thanks.
Right.
Thanks.
Yeah, I hope that cleared it up for everyone. Yeah, so as I foreshadowed, can we link the semi-simple dualities to the volume growth properties of the moduli space in more involved examples? So take type 2B string theory, compactify it on a Calabi-Yau threefold, which gives rise to an n equals 2 supergravity theory. And if you look there at the vector multiplet sector, this is the very general statement that I was alluding to before. It comes in a second. You have all the physical couplings of this theory you can compute from the geometry through what is known as period integrals that depend on the moduli that are called T here, and expanding in an appropriate basis for the charges of the red T-branes. So the moduli space follows from the Kähler potential, computed in this way. BPS states come from wrapping D3 branes now on 3 cycles. So these are particles or black hole states in the 4D theory. In the mirror type 2a picture, you can think of these as D0, D2, D4, and D6s wrapping 0, 2, 4, and 6 cycles. And the duality group, which is the electromagnetic duality group that mixes up all of these charges, is really the monodromy group inside the symplectic group of this period vector. Okay, so how do you see the semi-simplicity here at the level of these general Hodge theorems? And the idea here really is that if you assume a suitable mathematical version of our compactifiability criterion, that if you assume this moduli space to be compactifiable, that then implies that the electromagnetic duality should have a semi-simple representation. So the precise term here is that this moduli space should be Zariski open in a compact analytic space. For the purposes of this talk, what it just means is that it's a slightly stronger condition on the moduli space. It only applies to complex moduli spaces, and it actually renders their volume finite, as we already know for Calabi-Yau threefold moduli spaces. So let me get into a little bit more detail about these Calabi-Yau moduli spaces, if there are no further questions. So
I do have
yeah, of course.
From your previous examples. So, for example, in some of the ones that you show, once you have like enough dualities and you quotient, you get like a finite volume or a compactifiable one. But the ones that were compactifiable from the very beginning, in principle, there's nothing that tells you that you can have like extra, maybe finite dualities that quotient farther, but leave it as you are. I'm thinking on the theory on the plain bottle one that you had R2.
Yeah, I see what you're saying. Yeah, it's a very interesting question. Somehow there is this distinction between flat moduli spaces where compactifiability really doesn't say much because you already have a polynomial volume growth at the right exponent. So it's, yeah, they're just demanding compactifiability doesn't say anything. Whereas on the other hand, for these curved moduli spaces, it's a very strong criteria. Yeah, it would be nice to understand better what causes this difference between having many dualities whenever there's a curved moduli space and then actually it always renders the volume finite, whereas in other cases a remaining polynomial volume growth is kind of fine.
Can I ask a follow-up to that?
Yeah, of course.
So even for the curved cases, right, you can think of, instead of dividing by SL to Z, taking a congruent subgroup thereof, which is smaller than the full SL to Z, and you would still satisfy your compactification criterion, I imagine, without seeing the full necessity of taking both S and T generators.
Yeah, very good point. Finite index subgroups of SL2Z, like the ones that we see all the time in F theory, they're all fine. Whatever is the finite index, that would just be an integer that multiplies the volume. But indeed, the volume would still be fine. Actually, the precise term for SL2Z, for subgroups of SL2R to render the volume finite is that it has to be a Fuchsian group of the first kind. If you're interested. And what that effectively just means is that the fundamental domain, if you think of it, can only touch the real line through cusps and nothing more. That's effectively what that condition means. Yeah, thanks for the questions.
From the point of view of the dualities that you're quotienting by, does it always reach a finite volume, or could it be possible that quotienting you turn compactifiable but not finite as in the volume?
Sorry, could you repeat? I didn't get the last part of the question.
Yeah, sorry. Is it possible that for negatively curved moduli spaces your quotient, you get compactifiability, but not finite volume, or in all the examples that you see, you actually get finite volume?
Oh, that's a great question. No, I don't know examples of that kind, or put differently, like in everything we checked, we've never seen anything of that type. That you started with a curved moduli space, but you actually somehow quotiented out all the negative curve directions, but you were left with some just polynomial volume growth directions. We haven't seen that, which is kind of intriguing. All right, so let me be more explicit about what kind of duality groups can arise in these 4D n equals 2 supergravity theories. And I'll fix the simplest types of example. So I'm thinking of just a moduli space that's a sphere with 3 punctures, 3 types of singularities. One we know very well. In the type 2a picture, it corresponds to taking a large volume limit, which decompactifies us from 4 to 5D. In the type 2b picture that I'm using, this is known as a large complex structure limit in the mirror symmetry. There is a conifold point, just a finite set of states is becoming massless. And at this point, you actually have a positive curvature divergence, whereas the rest of the moduli space will be negatively curved. And then at the remaining point at infinity, it depends on the example you're looking at. You can have another large complex structure or conifold point there. Or the new types that can arise is that you can have a finite order monodromy point, a Leno-Ginsburg point. With some say in the quintic, this would be just the Z5 point where it has some additional symmetries, this Calabi-Yau manifold. Or something which is known as a K point, where you would have an emergent string limit for this infinite distance limit. Now, the details of the geometry don't matter too much for this talk, but I just wanted to mention them for completeness. What does matter, of course, are the monodromies. So there is a very inconvenient way that you can always bring these monodromy matrices into. Where now kappa are and C2, well, kappa is the intersection number, C2 is the Chern class, and all of the data here is just geometric data about the mirror, or topological data, I should say, about the mirror manifold. And already here you can see very nicely that these examples will always give you a semi-simple duality group. And the way by which you see this very easily is this large complex structure monodromy is just lower triangular. So thinking of this as kind of sending all the magnetic charges down to electric charges. And then the conifold point precisely does the crucial map in the opposite direction, where it maps the magnetic states in the other way into the electric states, or it exchanges them the other way around, I should rather say. And then completeness for the duality vortices means that really for all of these duality elements, there should be a corresponding axionic string in the 4D theory. Where as we go around, shift the axion by 1, there should be an object that implements this duality transformation. So for the large complex structure point, these duality transformations are very well known. Here in the type 2a picture, what you're doing is no more than a large volume monodromy. And the states that are arising here, or the duality vortices that show up here, are just NS5 brane wrapping the divisor of the mirror Calabi-Yau manifold. In the type 2b picture, this would correspond to a Kaluza-Klein monopole. And then for the other monodromies, to me, they're higher, or to us, their higher dimensional origin is a little bit less unclear, but have been studied as regulator strings when studying the full axionic string solution, and not just one at a time. But back to the duality groups, can we say more? So from type 2b, we know that we can say a lot. So the precise term is that we can say that this duality group is known as a free amalgamated product, which just means that we have the 2 finite order monodromy points, So we have the Z4 elliptic point, we have the Z6 elliptic point generated by the S and the ST transformations of order 4 and of order 6. And this amalgamated part just tells you a little bit about that the -1 element is in both of these Z4 and the Z6. But more interestingly, it raises questions, right? Like, okay, we have this duality group. It's generated by finite order monodromies of some finite distance special points in the interior. Can we always do that? The answer is no. The answer, I should say, is no. But we can actually lay out the structure of the monodromy groups in a very similar way, so we can answer this question very precisely. So for 7 of these 14 Calabi-Yau threefolds with this type of moduli space that I just showed you, mathematicians computed the monodromy group, and they found that it can always be given by these kind of free amalgamated products. So the first generator here always corresponds to the conifold monodromy or the large complex structure monodromy. You can choose these because you can always trade one of the generators of the 3 generators. Here in the Z times Z, the second monodromy would be a large complex structure or conifold monodromy. That's just what it is in these examples. And in the other 2 cases, you would have a Landau-Ginzburg monodromy of order 4, 5, or 6, where divided, where in the even cases 4 and 6, you would have a, sorry, I should say, I'm mixing it up. The second row corresponds to the quintic, which is Z times Z5. And in the other cases, K equals 4 and 6, you would have a Z8 or a Z12 monodromy. So what does that teach us? Well, first, let's look at this total landscape. So the volumes we computed, and they're all finite and actually rational in units of pi, which fits very nicely with this axionic string picture and the deficit angle they create at infinity. In 2 more cases, they are actually known as very precise arithmetic subgroups of SP4. But I'll spare you with the details on those guys. But the first lesson that we learned from this landscape is that duality groups actually cannot always be generated by finite order elements associated to finite distance points. Because in all of these examples, we need a conifold monodromy. That's still a finite distance point, but it's not a finite order monodromy. Secondly, actually, even this finite distance requirement is not a necessity, because there are examples where the duality group is generated, has an infinite order monodromy as generator, which is precisely this 4th row here, this Z times Z monodromy group, where you have 2 LCS points. So you can choose to generate one of the 2 monodromies by a conifold point, but the other one always has to be generated by an LCS point, so an infinite order monodromy point. And finally, you might have hoped that there's some notion of completeness of duality groups, which says that they should be of finite order in the largest group that it could have been, SP4. But actually, in all of these freely amalgamated cases, all of these 7 cases that I've been talking about, the duality group is actually of infinite index. Curiously, though, there is still a suitable mathematical notion of denseness here. And all of these cases are still Zariski dense in their terms in SP4. And the reason why this can happen is that even though these monodromy groups are not at all algebraic, so you cannot define it by just some simple polynomial equations, what they do is they take a suitable closure of this space, algebraic closure of this space of monodromy groups. And from that, you find that you still recover the full SP4. But we don't have a good physical understanding of why you would care about such a closure, so that's why I just put it in parentheses here as a small remark. So the upshot is, or rather the takeaway is that all these lessons that we have from SL2 which where you could maybe consider a finite index subgroup, where you could maybe consider just finite order generators, they don't seem to carry over to the more general duality groups that we see in the string landscape, where here we have infinite order subgroups generated by infinite order elements associated to infinite distance points. So really that is all special to 10D type 2B, and not at all the generic situation that we have in quantum gravity.
Sorry, Damian, can I ask? Could you say
Yeah.
that? Would you say that at the conifold point there's an unbroken Z-gauge symmetry?
Yeah.
But would you say that, then you would expect that by completeness principle, or at least unitary irreducible representations, have physical states transforming under them? And there's a continuum of those, right? They're labeled, well, almost a continuum. They're labeled by rational phases, right? E to the I, Q times N, where Q is a rational number. So
right.
it seems there's infinitely many states, and if this was an unbroken gauge symmetry, I mean,
you're saying you would have an infinite spectrum if you would really think of this as a Z gauge symmetry there.
Yeah, that's what I'm saying. In the conifold, it's a bit funny the way it acts. No, it's not like the discrete symmetries in type 2B that you were talking about, right?
That's true. Yeah, it's really a different monodromy in how it's not the usual tau going to tau plus 1, and you have just the standard electric and magnetic states that you're shifting. It's doing really something more to the field theory states.
Right. Exactly. So I don't understand the details, but I would say this is qualitatively different. At least there might be the least you could say is that there's perhaps two notions of what discrete gauge symmetry means. One is this one, and it's fine. And then there's the sort of like the more naive natural notion, which is you have a Z gauge field, and you have, by completeness principle, you have Wilson lines in all representations of Z. So that gives you infinitely many states. Or you have also this infinite dimensional representations you were talking about. All those states would be degenerate in mass, so you will have a problem with species. So that second notion is bad.
Oh, I see. Yeah, but that is not.
I mean, a symmetry in the usual sense.
No. Yeah. No. I see what you're saying. But if you were to impose a cutoff on this theory, which it needs to have, then actually at the conifold point, up to the cutoff, there are only finitely many states, because the Z that's generating states for you is not acting on massless states. It's acting on a massive state. So you're actually.
But even if it's acting on the massive states, let's say that you have the representation of Z that you were giving us, the one by the matrix, 1, 1, 0, 1, like the T.
Mm-hmm.
So suppose I have one physical state of mass n, non-zero mass n. Then I act with this guy. Since it's an unbroken symmetry at that point, produces another state with the same mass, okay, and has sort of like it's different from the first state, right? And then I act again, and I get a third state with the same mass, and I keep on acting, and I pretty soon get infinitely many states, which are all degenerate in mass.
Well, there's a bit of ambiguity here. Let's just, in the conifold case, it's the theta angle being irrelevant, correct?
Right.
Because you have a massless electric charge state.
Right.
So in that context, it's going to be a little bit ambiguous to know whether you're calling dionic state or not, because you have charge but doesn't have a mass. And so that's
indeed. So there's no states transforming physically under this representation I was just.
I think you could say it. There's infinitely many states have the same mass, because you can have charge 1, charge 2, charge 3, charge. They're all massless.
But they're all physically the same state.
No. You have different electric charge states. I'm just saying that the monodromy you're talking about, like with an effect, you take a monopole and picks up electric charge as take theta.
Yeah.
Here, that's true too. But the thing is massless. The electric degrees of freedom that you're going around is massless, so it doesn't affect the mass of the monopole. So the central charge of the monopole doesn't change.
But Kumram, because of Bekenstein's bound, you shouldn't have infinitely many states within a given mass range.
No, there's not infinitely many. All I'm just saying is that you have a massless electric state. If you have two of them, what do you call them? Do you have massless two electric states? What charge spectrum? You have infinitely many charge states with massless.
Yeah.
That's all I'm just trying to say in this language. A little bit because of that feature.
Yeah, I'm just saying there's two national notions of discrete gauge symmetry. This is one of them for the Z. But yeah. Thanks.
Right. Okay, so are there any further questions about this particular landscape before I move on to the bottom-up argument? If not, okay, so how we've been using this compactifiability criterion now and getting dualities from it, but why does it actually need to be there? And the principle that we'll get it from is from demanding finiteness of quantum gravity. So finiteness of Clabiau manifolds is an old topic. It has been proven for elliptic Clabiau manifolds, now in arbitrary dimension, even recently. It has been used in the context, or it has been turned into a physical argument for 60, or there has been developed this physical argument for finiteness in 60 supergravity. And also there's a mathematical proof of finiteness of flux vacua. But what I'll rather talk about today is really a very particular notion of finiteness, where we'll look at quantum gravity theories or reduce them down to a 1D quantum mechanical systems, and we'll demand finiteness properties of the amplitudes of this theory. And particularly, we'll demand that the number of ground states of this 1D quantum mechanical system should be finite. So you may ask, first of all, why? Well, first of all, even at zero temperature, you would find that the entropy of the system would diverge. And also, even at finite temperature, the partition function, due to this infinite number of zero modes, would diverge. So how do we, but how do we actually characterize these ground states? And for that, there is a very helpful way by Witten, where the ground states you can get from fluctuations over the moduli space. So the precise way that works is that if I take an harmonic normalizable P form on my moduli space, then I can actually equivalently turn it into a ground state, as shown here on the right, where all of these harmonic and normalizability properties of these differential forms map to the necessary conditions that we need for the quantum mechanical ground states. And now the key question is, can we relate the growth of the volume to this spectrum of ground states? So when the growth of the volume is more than polynomial, more than Euclidean, can we really see that there's an infinite number of ground states? And the answer is yes. So for a matrix of this form, so asymptotically, so you go into the asymptotic regions of moduli space, and it takes this standard spherical form with an r to the t plus epsilon, where epsilon measures the violation of Euclidean space, or the violation away of Euclidean space. We find that there are infinitely many harmonic modes precisely when epsilon is bigger than 0. And in that case, you see precisely that if there are these infinitely many modes, you see that the volume grows more than this Euclidean volume growth. And as an example, so let's go back to type 2b, so the standard upper half plane, no duality group at all. In that case, these harmonic normalizable 1 forms on the upper half plane are given by this way, and you can check that they're all massless and all normalized in the right way, and thereby give rise to this infinite spectrum of ground states for the 1D quantum mechanics associated with. There is one subtlety here that I swept so far under the rug, but of course you may ask, well, we compactify on the torus, but what about the moduli of the torus? Because in principle, they mix with the other moduli. In this kind of way, where the moduli space of this 1D quantum mechanical system is that of the quantum gravitational higher dimensional theory times that of the torus. And this mixing can come from loop corrections, can come from instantons, from all sorts of effects. But to say something about the volume of the moduli space of the original theory that we're interested in, it suffices to look into only what corner. So if you look into the large radius corner, this mixing, which I denoted by a semi-direct product, really goes away, is all suppressed in the large radius limit, meaning that the metric really factorizes in this way, so that if the moduli space of the quantum mechanical theory is compactifiable, That means in particular that from this one corner, also the moduli space of our original quantum gravitational theory should be compactifiable.
So, Damian, can I ask quickly
Yeah.
about? So the ground states you constructed anymore are now, once you take into account the d-1 moduli, they are not exact ground states, no? They can leak a little bit on those. That's what you're talking about?
So I'm not thinking about the ground states. At this level, I'm thinking just about the moduli space. So just demanding compactifiability, just demanding finiteness of the ground states of the quantum mechanical theory, so the full system, that ensures that this full moduli space is compactifiable. All I'm saying here is that compactifiability of the full quantum mechanical moduli space is enough to say that also this one corner should be compactifiable, and therefore the moduli space of the higher dimensional theory.
Okay, thanks.
Yeah. Yeah, it would be interesting to do this at the level of the ground states, but here I'm just talking at the level of the moduli space.
Sorry, can I ask a question?
Yeah, of course.
Yeah, so how robust is this argument against, let's say, adding a small mass term? If you have a moduli space that already violates this compactifiability, but then you add like a really tiny, scalar potential that would make sure that the number of absolute ground states would be finite, like it would reduce them to a discrete set, would that pass this compactifiability test?
Well, I mean, it depends a little bit how I want to incorporate the scalar potential into the story, right? If I interpret this mass term as just stabilizing this mode, to just say, by mode I mean the modulus here, so saying that this modulus is just fixed to phi equals 0. In that case, I mean, the moduli space is compactified just by having the mass term. But of course, it would be interesting to think more generally how to incorporate the scalar potential into this story and say something about mixed directions where the scalar potential is doing something, but the moduli space is also having a large volume growth or something.
Yeah, because my concern is that if you have like really light scalar fields, that if you look at the, the potential doesn't, let's say, diverge. It's not just a mass term, but it's just a small perturbation that everywhere remains small. And if you look at the scalar field space of the light scalar fields, it can, violate the compactifiability. But then when you add the potential, the grounds, because it stabilizes the moduli, the vacua might, satisfy the compactifiability. Because of the scalar potential. So adding a tiny scalar potential on an exact moduli space might make it okay.
You're saying that would maybe kill the infinite number of ground states that I like. Oh, I see what you're saying.
Yeah.
Well, it would kill it, Alec, but we don't have that liberty. I mean, this is not a field theory. You're given a theory. You cannot control what you're given. Now, if you're asking, and the argument that Damian is talking about is only true for supersymmetric cases. So the only cases where you're talking about will be, let's say, like n equals to 1 superpotential case, where you can add a superpotential term and still give some kind of a potential. That's the only context. Otherwise, of course, it's a good question, what happens when you have no supersymmetry? He's not talking about that case yet. In other words, the discussion here, when we talk about the ground states of the quantum mechanics, has to do with supersymmetry. So if you then restrict to n equals to 1, then the statement is also very precise. Namely, the statement will be replaced by the statement that the space of covariant dw equal to 0, that space should be compactifiable. That statement, that's a precise statement in that context. D of w being 0 is what you want to be compactifiable. That's the precise statement.
I see. So we're really looking at the vacua. But yeah, in the non-supersymmetric case, I mean, it sounds like there should be a generalization of this, that you can probably consider light scalar fields, but yeah, it's hard to see how the argument goes.
Just so that we are clear, if you take a hyperbolic one, and if you just look at the spectrum of the Laplacian, there are no normalizable states. It's crucial that there's a one forms we're talking about. So this is the space of all this ground states is relevant for the discussion. So it's really at least the argument here is very much geared in the context of supersymmetric quantum mechanics. So the generalization of this is not yet completely clear.
I see. Thank you.
Right. So since I'm almost over time, I think we're out of time. Let me move to the conclusions. So in the first place, I've told you about how compactifiability of moduli spaces gives a very interesting, powerful bottom-up principle motivated by finiteness to constrain EFTs. And it tells us both about the presence of dualities, and it also instructs us a little bit already about the form of these dualities as semi-simple representations. Of course, it would be interesting to have a more general argument about completeness of states that tells us why this duality representation should be the way it is in all of these examples. It would be interesting to make a bit more precise how does curvature of the moduli space come into all of this. So we've seen these flat moduli spaces with polynomial curvature growths, but we've seen curved moduli spaces with many dualities resulting in a finite volume. What is precisely the underlying reason there? And of course, but much more complicated. So what can we say about moduli spaces with scalar potentials, like what we just discussed? Thanks.